Welcome to chapter 36, variable frequency control. This is where we get down to the meat and potatoes of variable frequency drives. How do we control the speed of a synchronous motor? Well, the speed of a synchronous motor is the function of the frequency of the three-phase electrical power we're sending to it and how many poles it has. And so a two-pole motor, as you see here at 60 hertz, spins at 3,600 RPM. As the frequency goes down, the motor spins slower. And as we add more poles, the motor spins slower. Now, it's impractical for us to change the number of poles in a motor on the fly to change its rotating velocity. So what we can change, though, is the frequency of the AC waveform that is being fed to the motor. Now, if we change the frequency of the synchronous AC motor, this is going to change the inductive reactance of the motor. So remember, a motor is a series of coils. These coils produce magnetism. And inductive reactance is the function of the inductance and the frequency. As the frequency gets lower and lower, there's less and less inductive reactance. So to prevent the motor from getting into an overcurrent situation to where it will burn up, we also have to reduce the amount of voltage. So if we have a low frequency, we have to have a low voltage. So here are some methods that we have for doing variable frequency, or to cause, therefore, then variable speed of motors. One way is to use an alternator. Now, an alternator is a rotating machine that we can control the RPMs on, and we can control how much excitation is going to the stator. The stator excitation will control the voltage level, and the rotating speed of the alternator will be the frequency of the output waveform. So this is an old school way of getting, say, a conveyor belt to be variable speed, where we'll have multiple induction motors on the conveyor belt. We will have a variable speed DC motor driving the alternator. Now, this alternator, the way this dyno motor is going to work, which is the DC motor connected to the alternator, we're going to use the eddy current clutch that we saw a few chapters ago. And we're going to adjust the output voltage on the alternator by adjusting a DC power supply that's feeding the stator windings. So let's get to the real thing. This is a simplified version of a variable frequency drive. And this is for solid state control, and this is what is in the heart of a VFD. And it actually has three sections. The first section is a three-phase bridge rectifier. And this three-phase bridge rectifier is taking in our AC power and making it into pulsing DC. The second stage is the filter, and that's this inductor and this capacitor. And here we're filtering the ripple out of the pulsing AC to turn it into DC voltage. And then here we have our H bridge. And these solid state devices are going to turn on and off in different pulses. Now, these pulses are going to be full voltage pulse off. Using pulse width modulation, we'll then develop our rotating field for the motor. So here, in this third section, we're actually going to be recreating a sine wave using a mathematical function of integration. So what is the output waveforms? First, we've got just a simple balanced pulse, on, off, on, off. And we can have a modified sine inverter that will do just this, and that is enough to drive a motor if the pulses are fast enough and we have a small off gap here. Here we have a stepped wave where we've got two voltage levels that are kicking on and off to give us an even closer modified sine wave. But the motor we were just looking at, the system we were just looking at, does this, pulse width modulation. It'll be pulsing up and pulsing below, depending on which set of the IGBTs turn on. And then we're going to adjust the width of the pulses. And so we see here in this first pulse, it's not on the full time, but the sine wave is very low. And as the sine wave is supposed to get greater, the pulse widths get larger. And so this way, if we were to do this, the summation of this pulse width modulation here, it will give us the sine wave. This is how we recreate it. Now, because it's square waves are rich in harmonics, and we're going to get into that in just a second. So let's first talk about some of the issues with the reconstruction of sine waves. All methods cause harmonics, and harmonics are waveforms that are to this every other one, every third, every fifth, that are going to be repeated. So I'm going to show you an example of what the harmonics are, but all square waves are rich in harmonics. This has to do with Fourier analysis. Now, the three methods that we use for recreating the sine wave, these solid state devices, we use SCRs. And of course, we say they can cause harmonics, and that those harmonics can cause problems in the system. And SCRs will also have issues with being turned off, because once you click on an SCR, it does not go off until the waveform drops below 0. So SCRs we're only going to see on the input side of the VFD. Bipolar junction transistors, or BJTs, and IGBTs is what we're going to see on the output side. And so for BJTs, they usually have a very high resistance internally, where they'll have a 0.7 to 1 volt drop. And this can cause a lot of heat to build up. And they have slow switching times, meaning how fast it takes for them to transition from when we turn them on to turn them off. IGBTs turn on and off much quicker. They have an even lower internal resistance, and they have a high input impedance, meaning that when we send the signal to it, the signal's not actually being affected inside the path for power. So why are there harmonics? Well, this is our formula here for a square wave. This is a Fourier transform. And so our resulting square wave is the infinite sum of the sine wave function here. And so this k, we start at 1, and as we go through each click, we're adding to k. Now this infinite sequence, when we work it out, works out to this. We've got the primary sine wave, then the sine wave times 3 to 1/3, the sine wave times 5 to 1/5. And so this is going to grab every odd harmonic all the way down and sum them up infinitely. Now I'm not able to do an infinite sum here, but here's a little Excel graph. Here we've got our primary sine wave. And we are going to add the first harmonic. So this is 3, x of 3 to 1/3 amplitude, x of 5 to the 7th, and to the 9th. So these are all harmonics of the primary wave. So these are all signals that are on the system at the same time. Now, what the Fourier analysis says is we're going to add all these together. So it's the infinite sum of these is going to create that new waveform. And that new waveform, that summation, looks like this. This is our, so it's not perfect, but as we add more harmonics, this levels off and the steepness of the transition increases. So the summation of the first 5 harmonics gives us this, nearly a square wave. And so this is why we say square waves are rich in harmonics, because it's the summation of all of those alternate elements. So here we have the IGBT version. Notice we're just using diodes here. And our symbol for the IGBT is different. And it's got this double bar here. This is that high impedance that we're talking about, where no control current is getting in here onto the collector. And then here's our DC portion, the choke and the capacitor. So now that we've talked about the VFD, that they're rich in harmonics, and we have to be able to control those harmonics. And to do that, we need to have an inverter rated motor. And so these are going to be for continuous operation. They're going to be in a larger case than a regular three-phase motor. They're going to have extra insulation around the wires for each winding and with the stator core. And we use paper for that. The wire that we wrap it, we call it magnet wire. What magnet wire means is that the wire itself is insulated with varnish instead of a plastic piece. And what the varnish does is provide the voltage protection, the insulation from the wires from shorting out, but it's also super thin, so we can pack the wires in much closer. And the closer the windings are, the stronger the magnetic field. So we have another type of a solid state device, a GTO, and it's a gate turn off device. So it's similar to an SCR, but it's on all the time. And the signal we send to it is when to turn it off. And we use these for motors rated over 500 horsepower. And they have an even smaller internal resistance on them. So it's just like an SCR, except it gives an off signal instead of an on signal. So here we have an example of how the output side works with a load for a variable frequency drive. And this is similar to a project that you did in B1A. Now what we have here is this is a single phase, example of a single phase, not three phases, just a single phase. So here's the DC supply portion from the variable frequency drive. And here we've got our kickback diodes for the changing frequency. And so when we want this, when we turn this on, SCRs or IGBTs or BJTs, A and A prime turn on first. And so here we have our path coming in, and it's going this way through the coil and leaving. Now, when we want it to go the other direction, we turn on the Bs. And so our path again is coming in, but now it's going the opposite direction through the load and completing the circuit. And so this is how we get the positive half cycle and the negative half cycle of our pulse width modulation. So here we have some features that we have with variable speed drives. We're going to have the VFD rated motor is going to have some sort of sensor on it that's going to provide us feedback to the VFD. We're going to have current transformers that are going to measure what's coming into the variable frequency drive. Now notice with the variable frequency drive, we're not having an overload. We don't have to put in reactors. We don't have to put in resistors in front of the VFD because the VFD is going to make all those decisions for us. So we just feed the VFD from a breaker, and we have the 1 or 3 current transformers to measure how much current is coming into the VFD. And the VFD will do the soft start, will do the frequency control, and will also sense overload conditions. So we see speed control, current limit, which is overload. We can automate the speed control. We can do our start and stop ramping. When we're going slower than 60 hertz, we have to reduce the voltage because of the inductive reactance issues. And we can actually get the motor to spin faster than its rated speed by putting in a frequency above that of 60 hertz. And it looks like I left an extra slide in there. But that is it for this lecture. Thank you very much.